All right, let's talk about a concept in calculus that can seem a little intimidating at first, the definite integral. But what if I told you that you can actually start solving them using geometry you already know? Yeah, really. Let's pull back the curtain and demystify this powerful tool together.
This quote right here really nails it. An integral isn't just about measuring some flat, boring area. You should think of it more like a running total. It's a dynamic accumulator, constantly adding things up, maybe subtracting a little, and giving you the net result at the very end.
Okay, that's a cool idea, but how does it actually work? How does this concept of accumulation help us find the area that's trapped between some function and the x-axis? Well, that is the exact question we're here to answer. So here's how we're going to do it. First, we'll cover the big idea of what an integral really is. Then, we'll get into the super simple rules of what's called signed area. After that, the fun part. We're going to use basic geometry to solve some integrals. Then, we'll tackle some more advanced examples, and finally, we'll talk about why this way of thinking is so incredibly important.
Okay, first things first. What even is a definite integral? Well, at its heart, it's just a tool. It's a really precise way to calculate the total net change, or what we're going to call the net signed area, between a function's curve and the x-axis.
And I want you to burn this term into your brain. Net signed area. It's the absolute key to unlocking all of this. See, we're not just finding the total amount of space. It's more like we're keeping a balance sheet. We add up all the positive areas, subtract all the negative ones, and see what the final balance is. So, how do we know what's positive and what's negative? Thankfully, the rules for this are incredibly simple. It's all about where the area is located.
It's really this easy. Just think of the x-axis as being ground level. Any part of the curve that's above ground, that area counts as positive. Any part that dips below ground, that area counts as negative. That's it. That's the rule.
So the definite integral, with all its fancy notation, is just the mathematical way of saying this. It adds up all the area above and subtracts all the area below to give you that final net value.
And now for the really cool part. This is the moment where it all comes together. We can actually solve some integrals without using any fancy calculus rules at all. We just need those geometry formulas you probably learned back in middle school.
So, take a look at this thing, the integral from -2 to 2 of the square root of 4 minus x squared. Now that function might look a little intense, but I promise you, you've seen it before. It's the equation for a shape you know very well.
Let's just break this down. The first and most important step is just recognizing the pattern. That function, y equals the square root of 4 minus x squared, is the classic equation for the top half of a circle. Since that number is 4, that means r squared is 4, so the radius is 2. So, all this integral is asking for is the area of a semicircle with a radius of 2. We don't need calculus for that. We just need the geometry formula, 1/2 pi r squared. Just plug in our radius of 2 and we're basically done.
And there it is. The answer is 2 pi. We just solved a calculus problem using basic geometry, just by recognizing the shape hiding in the equation. Pretty cool, right?
Okay, let's kick it up a notch. Now that we've got the basic idea down, we can start looking at problems that have both positive and negative areas we need to account for.
So for this one, we're integrating the line y equals 2x minus 4 from x equals 0 all the way to 4. Now, if you picture that line in your head, you'll realize it actually crosses the x-axis, which is our clue that we're going to have some negative area and some positive area to deal with.
And this is exactly what it looks like. Our function creates two different triangles. The first one, from x equals 0 to 2, is below the axis, and its area is 4, so we count it as -4. The second one, from x equals 2 to 4, is above the axis. It's a perfectly symmetrical triangle with an area of +4.
So what's the net signed area? Well, we just add them up. -4 plus +4 equals 0. The two areas completely cancel each other out. The value of the definite integral is just 0.
All right, one more example to look at a different property. What if you know the area of a big chunk, and you know the area of a small piece of it? Well, you can totally find the area of the other piece. It's just common sense.
So here's the scenario. Let's see we know the total area from 0 all the way to 5 is 12. And someone tells us that the first part of that journey, the area from 0 to 2, is 4. The question is, what's the area of that leftover piece?
Well, this is just simple addition, right? The whole thing has to equal the sum of its parts. So our total area, 12, has to be equal to that first part, 4, plus whatever our missing second part is. A little bit of subtraction tells us the area we're looking for has to be 8.
So after all that, what's the point? Why is it so important for anyone learning calculus to really get this geometric perspective on integrals?
Look, this is the big takeaway. Seeing the integral as this accumulator of signed area, it's not just a cute trick for simple problems. It is the core intuition. This is the bedrock that all of advanced calculus is built on. I mean, think about it. In physics, when you integrate velocity, that net signed area gives you your final displacement, how far you are from where you started, not the total distance you traveled. The negative area is just you walking backwards. In economics, integrating profit and loss gives you your net gain. This idea is everything.
So I'll just leave you with this question. The next time you see that long S integral symbol, are you going to see a scary formula you have to solve? Or are you going to see it for what it really is? A story of accumulation, of how something changes over time. Because now, you know how to read that story. Thanks for tuning in.